Hello, gentle readers, fellow Earthlings. February 8, 2026. Today from Study with Ross Finlayson. Here is Reading Foundations. These sorts of video essays are about an hour a piece. And so that's sort of just a reasonable unit of time compared to, like, the minute and the second, the usual notions of timekeeping. And then also, it usually works out that the video fits within 4 gigabytes, or gigabytes, as it were, with regards to 31 and 32-bit offsets, usual notion of the file system. Whereas then it's a bit simplified to then be able to transfer the file from the phone with its sort of HD TV camera, or SD 720p, as it were, in HD TV and standard definition, and then over MTP, mass transfer protocol, of the USB universal serial bus. That's just the usual way that the bits and bytes of the samples of the chroma and luma of the CCD circuit diodes make it so that then this sort of account, and combined with an audio track, which is really only a necessarily needful thing, is there's no particular diagrams or on-screen legend to consult. That these are the usual format of these sorts of video essays or lectures, and then there's how one might say a course of these, but this you can kind of explore for yourself. As with regards to reading in foundations, and then the foundations of reading, and as with regards to an account from 20th and 21st century physicist, logician, a mathematician, an engineer of according to the development of novel things for how one might say the library. That these are the usual things. So today I'll just be continuing reading from the stack of books, and then just offering some commentary to go along and help to both frame and focus the work and the author as an expert and an authority in their field. Because I pick books for people who generally I would regard as having at least a way to read them generously is correct. And then also, as with regards to sometimes being matters of the sole source, the ideas of being primary sources and then sole sources of relevant fields in these studies in foundations. And then there's the sort of idea, then also I'll try to frame it in the lens of kind of from this kind of holistic, a coherent account from here, so that that will just kind of be framed in the narrative of this wider context, the wider Fuller dialectic, as it's called sometimes here, of this A theory, a natural, axiomless natural deduction and axiomless geometry, and then an axiomless language, in a sense, for the Comenius language and Coleridge language, and these other aspects that go into, for as after a principle of inversion and principle of sufficient and thorough reason, an account of logic, and thus a stronger mathematical Platonism, a stronger logicist positivism, that then thusly these sorts of accounts combine to then address for the singular sort of thing, which are foundations, the theory of everything would be, would entail having to be a monotone sort of account. And so then as is mentioned generally and broadly, is that the supreme and the omni are separate, unfalsifiable to science concerns, while as well there is yet this briefest, merest teleology, which is as for matters of causality and purpose and the determinism in the world, and then balancing that generally with the ontology and the analytic as of the course of one's own deliberation and contemplation of the matters. That's free will, and for these sorts of accounts of will and independence, largely is for independent will. and thusly responsible will, not just the randomness or the discontinuity or the capriciousness of the less than the arbitrarily, judgmentally sound sort. So let's see what's in the box. What I see here in the box is this is P.C.W. Davies. So I think this is the same as Paul Davies. Space and Time in the Modern Universe. This is a fantastic book for the study of special relativity. Cambridge Press, Davies. And so sometimes you'll see the author as, it just says Dr. Davies. And I wonder sometimes, like, well, sometimes I see P.C.W. Davies. And other times I see Paul Davies more modernly. And so if you had written this, this is 20 or 30 years before 2000. So this I think was from about 1980 or so. It mentions, for example, J.W. Dunne. A few years ago, some very unusual books were written by J.W. Dunne on the notion of serial time, based on the idea that a moving time must be measured against another time to make sense, e.g. how fast does time move. Dunne proposed an unending series of time dimensions, each one engaging in a flux relative to the next. In support of this extraordinary proposal, the author cited examples of apparent precognitive experiences associated with dream states. Although Dunne's ideas have not been generally accepted by physicists, it is curious that the latter always seem very reluctant to deny the reality of a moving present. Unless this moving now phenomenon is to be discarded entirely, it has to be admitted that we do not understand something about time or about the mind, or both. In the emerging picture of mankind and the universe, the future, if it exists, will surely entail discoveries about space and time, which will open up whole new perspectives in the relationship between mankind, mind, and the universe. So that's the end of this book, and as begins the index from absorber theory of Wheeler and Feynman. So for like FLWR, Feynman, Wheeler, and then FLWR theory, Rudolf Clausius, damping, de Sitter, density, Robert Dicke, D-I-C-K-E, Paul Dirac, D-I-R-A-C, Friedman, so not Feynman, Friedman, models of the universe. So that would be where the FLWR, and that's a pretty successful model is the FLWR bit. And then Galileo Galilei, some mentions of Hawking, Fred Hoyle, most known with Bondi, as about the steady state hypothesis in contrast to the Big Bang hypothesis, both those being unfalsifiable and both those being fittable to the data, as after the account of redshift distortion and redshift bias, that these days, since James Webb Space Telescope and including what now is being kind of retrofitted in the data of the Hubble Space Telescope, is after 2MASS and Eötvös, and what's coming on forward is the newer accounts and what's going to be the Nancy Grace Roman wide frame imaging. The Sky Survey has largely made it so that there's a great difference between what the world saw as redshift in the Sky Survey of the 1920s in the time of Lemaitre and Eddington, which made for Big Bang Theory, and the what results of steady state theory. That here is to be then, as after something like cyclic cosmology, and if that's for like Penrose and that, where they're just trying to say is like, well, if it's Big Bang Theory, then how can it also fit these models of where it comes and goes, and the various notions of the birth and death of the universe, as it were. Then there's kind of like for Newton, and then Fadio-Lesage, and then Einstein, and then kind of a FitzGerald and fall gravity of a sort, or fall gravity, F for fall gravity in this case. There's for Bondi and Hoyle, and it's much like there's for Lemaitre and, say, Eddington, say, or Einstein, or Finley Freundlich, or otherwise, according to Hubble, Lemaitre and Hubble, that there's these are the models. And so what's standard today was once nouveau. And then what's classical and passé is again super classical. And so these are the sorts of accounts, and as to why then when looking at this book, it's really got just some great accounts. And when I read this, it gave to me what I thought was one of this was when I was reading this book in the middle of it, I thought to myself, I finally understand why length contraction and time dilation get associated with special relativity. And it wasn't just because, well, by mass energy equivalency, nothing can approach the speed of light. And so as it goes faster and faster, according to the inputs that go into it, it would just kind of peter out these other inputs that would go into it. But these are kinds of the ideas of the thing. So it says here, this is first published and reprinted in 1977, R. Donnelly and Sons, for Cambridge University Press, Davies PCW. Space and time, Newtonian space and time, Mach on the relativist or the relationist view or the relativistic view. Mach is given as kind of a kind of a wider account, the Mach-ian, than the classical. It's a potentialistic theory, and furthermore, the outside of the potentialistic theory. About Mixon-Morley and the ether and Einstein. And of course, here, as is noted, Einstein, by 1935, in Sidelights and Relativity, had made it so that he definitely declared that ether is a thing. And with Einstein and Infeld, that ether is a thing. And Einstein has a clock hypothesis. And Einstein separates and distinguishes and makes a contradistinction between the spatial of the usual notions of curved space-time, the spatial, and the spatial. That what he does, that's for light, that he then gives all the kind of the fallen apart bits, and that light would kind of point every which way. That goes to the spatial, and then the spatial, that's usual count is after the Galilean and the Newtonian and everybody's usual apperception of flat space-time. And so that's being considered here, being written up by Davies in this book as part of the background necessary to describe what goes into this and why it's so relevant. And then he gives some examples of either numerical coincidences or otherwise kind of the ideas of orbits, and then about why that some of the numbers are like as relating to things like Bode's law, which is like, well, according to the model of platonic solids and how they fit in each other concentrically, kind of like as after accounts of Conway on Bode's law and notions of polyhedron and how they fit. Then the planets seem to line up exactly like that. And whether that would be similar or the same in many, many, many solar systems, that with regards to this being kind of like the Terran system, whether Terran is the planet, the Sol is the sun, whether it's called the Terran system. All these kinds of different solar systems would have the planets, their size, composition, and their distances kind of not randomly the same by a natural sort of association. Kind of like with the consideration of electron bonds in their orbitals, that they kind of follow a pattern. And so that it has some of these things are addressed in this book or in another book by at least another of the same Davies, and this kind of thing. Some algebra, differences in T1 and T2, and then proper time, and these kinds of things. And the phenomenon of clocks, the twins paradox, and these kinds of things. So here it's figured that for, like, as the quote from the end of the book was getting into, it's like, well, what is time, and how can it be? And then it like over the past decade or so, one outfit was kind of like, well, they got the A and the B theory of time, and then there's one guy who is trying to say it's like scattered everywhere, this that. Here the clock hypothesis is the idea is that there is a universal time. In the cosmic clockworks, there is somehow a given state of the present. So what's done is done, what's in the past is past, the future is not yet written, we're always in the present, which is now ongoing. And so then whether clocks, the notions about the time dilation is like, well, do clocks just change their speeds? It's like, well, yes and no, because you can just say they always change their speeds, but if they only ever slow, then that makes for an account of space contraction that makes it so that you say, well, I have a theoretically acceleration across space and time that when I arrive, my clock will have not gone on. And then compared to observers in the past, according to the travel and the path, that their clock would be much, much greater, is that by the time you turn around and went back, it would add back up the other way. You could just consider it from either of two relativistic positions. It's kind of like so compared to like a photon in the whole universe of things, or a photon, one event or particle or sample in an entire ring cyclotron kilometers wide or something like that. That makes for the differences, and why otherwise there's a certain symmetry, according to time dilation is part of always length contraction, not always part of space contraction. For real space contraction linear and real space contraction rotational is kind of described in these podcasts. That the light then, and then as with regards to the clocks, that being the account is after special relativity. That's the only thing within special relativity has as its senses. Those are the only inputs that there are in that theory. And here that's like after general relativity, not before. So it never stands by itself. Special relativity, restricted relativity is also called. That then the clock hypothesis can still have clocks can meet. Because usually clocks just meet. Whenever there's two clocks together, they are synchronized by as a matter of fact, they observe according to all matters perspective the same things with regards to like front and back and receding and approaching and these kinds of things. And you got Doppler quite naturally and built out of it all the same way. As regards to either one, it would be independent to flip a coin and see whether or not they're on the one side or the other, and they'd be indistinguishable in this way, while there's yet a contradistinction of each way. So clocks meet, and so that the usual account for everybody who thinks that the world is on time and there's a system of the world is that's just always so. And then the other idea is that clocks slow is the idea that when a certain particular thing can be retarded, slowed, in its evolution, otherwise according to time terms, because the laws of physics are the same everywhere. That's according to contrivances of the configuration energy of experiment is the idea. That the having that clocks only move or only slow or meet, that clocks only slow or meet, makes it so that in this way, then there's the space contraction is real, and it's always length contraction and time dilation put together, and as for accounts of FitzGerald and Neumann and others invented these ideas before it came out 40 or 50 years later in the 1920s after 1905 and this kind of thing. That the FitzGeraldian account of space contraction proper, and that being about electrical fields and the electromagnetic and the electrostatics and electrodynamics, space and the ether, that there's this way that context is not so on the surface, or perhaps even in the depth of this author's work about space and time in the modern universe, as is the title of this book. And that space and time in the modern universe then has those as just kind of like the sliding rules of these sorts of accounts as after the theory was like to so, but since 1977, a lot of that has been falsified. Dark matter and dark energy have falsified the cosmological models, and that includes the model of gravitation and the model of light. So then how that's put back together to say, well, how is general relativity and special relativity for then all how it is shown to be so? How does that hold up? And it was not just contrived to begin as from our terrestrial frame. Then here that's for kinetics. The kinematics is different. Momentum is only pseudo-momentum, is not conserved except in the overall potentialistic and in the open systems. And then for light, that the redshift bias and redshift distortion basically represents this sort of redshift rewind, or the notion that much like the path integral is for an electron to follow as a particle away of all its possible paths, that the redshift travels according to the ether drift, and that kind of adds up for what Earth's speed is in the universe according to all the light that it gets from everywhere. It's just kind of the speed of light observed is just twice that in the terrestrial, and it's always been that way because all experiments and measurements have always been from the terrestrial. The light speed is still a constant in deep space. It's arbitrarily large, kind of. But then as it enters particular gravitic or gravific systems, it has gone around many, many times that the geometric of the laser beam as being a monochromatic and perfectly linear compared to the incoherent light, as it's called, the optical, is that the optical is this fuller Fresnel account that Fresnel for optics gives us, and for Arago and these sorts of things that the mathematics already does give why and how that could be so. And so it fits back in special relativity. And then for general relativity, the dark matter fits back in general relativity as the Newtonian and the Galilean, again, plainly, because the accounts of space contraction linear and space contraction rotational are made contradistinct. And then this way, there's also that the world's turn bit makes for so why otherwise this theory overall can be a one theory itself and good. So this being mostly for the side of a relativity theory or GR, and then for quantum mechanics that's not really addressed in this work, but it has here, for example, it's built upon the statistical ensemble and the second law of thermodynamics from irreversibility and thermodynamics. That's a quantum mechanical, a statistical mechanical account. And this is a great book, thusly, as a survey of the field, and it kind of a way for the author to relay all these kinds of things, and as well to give where it's so demonstrated that when he's saying something, he by default he'd have to be able to say, no matter what I say, it has to be related to everything else I've ever said. So if you can find any contradiction between what's said in this book or what Paul Davies or PCW Davies says in some other book, then you can call him out on that. And so having a kind of a coherent account overall is perceived as being necessary. Now about Friedmann and Wheeler and Feynman and Wheeler, here's this, it's Feynman and Wheeler have been talking about, this is the absorber in the future. And so the absorber theorem is a great sort of account, is like for acceleration and the advanced and these kinds of things. Because that is kind of the leading edge of what makes for the space contraction and what would add up as being these compressed pieces in the front. Vis-a-vis like then that basically makes for the models of warp in space and time, the warp and weft of the space in time. So the absorber as a mathematical thing, it gets a quite long descriptive treatment. And that's why there are no closed time-like curves. Yet space-time is flat, yet it is a gauge theory. The theory is a gauge theory. That's usually after it's said that, yeah, according to all of big science's big data, physics at all is a field theory. Then, and for the nonlinear, then it's like, and it's a gauge theory, which is just a field theory with where the gauge after the metric and norm is its own thing. The idea of a cyclic world is at least as old as Aristotle. In more recent years, the general theory of relativity has yielded a number of situations in which the future histories of objects apparently join up with their pasts. Maybe as of energy, I was like, it's like ashes to ashes and that kind of thing, but not the same as it's like that out of it can result the same thing. And there can be models of mathematical resources as well. Space and time is just a continuum and an infinity, and then be able to say is like, well, we're constantly each other's echo, or we're constantly each other's parallel wide thing. The usual idea for time, chance, and uncertainty is that's always collapsing. So something like Penrose's explosion of the combinations, and what makes for stuff like the multiple worlds interpretation is like there's too many possibilities. For them to all exist at once is they don't all exist at once. The chances all exist at once, but they're constantly annihilating, and then there's just matters of fact, and causality remains in any account with the Clarke hypothesis. And then whether or not that allows free will is like, it doesn't really matter, because it's unfalsifiable that human beings would or would not know that they have free will. Thus, arguably, they do, because it can't be said they don't. And that they wouldn't at all wouldn't even raise the question. But this is a great book, though, and it would be an example of how he can point to that and say, I know what I'm talking about, and this is related to all these other aspects of all these other authors in the field and what they say. So then, with regards to trying to make a new kind of statement, here it's that it's not really read off from that anything that does, but at the time it would have been in the course of development, ideas and theories and these kinds of things, which so often are just kind of like a field and a possibility and the idea of something that could be kind of written out and written off. But here for foundations, it's either got to fit all the data or that mostly that it doesn't. So these are the kinds of accounts. Here's a good little book here, Our Radiant World. So this is about the nuclear energy, and so all these accounts of relativity theory for kinetics are for mass, the quantity, and all of them for electrical force are charge, the quantity, but the lifetime of the proton and then the speed of the photon, or the lifetime of the neutron, say, which one of those nucleonic particles is kind of singular elementarily of the atomic number vis-a-vis the species and the isotope and the atomic mass of the things. It's usually about atomic mass units, and then neutrons, an atomic mass unit usually being I think that it is the mass of a proton and electron together, which still has that the electron itself is always a charge to mass ratio. And then the proton would be too. And then for the lifetime of the proton and neutron, they're arbitrarily large, yet finite. And so light speed is finite. Another notion of relativity theory is kind of like a neutron's lifetime is infinite compared to light speed is infinite. In deep space, in a vacuum, and then for a neutron is like in the center of the universe. Thusly, this sort of tetrad of quantities makes for then in our local, it's really mostly about matter and charge is representing the surfaces in the stoichiometric of the elements. While light's free flux basically is the matter of measure of meter of remote sensing at all, and whereas as well the whether the clock is the atomic clock and how that's to be is for this tetrad of quantities. So the tetrad of quantities is raised here often enough because it's like, well, there are four forces, or there are those as four fields, or there are four subatomic particles, photon, neutron, proton, and electron, or there are four classical elements, or if they're fire, water, and then adding the void or adding the pneuma or these other sorts of counts. Or there's three states of matter, or four, gas, liquid, and solid, plasma, and the various notions of the super of those with regards to these things. That these notions of the supersymmetries and the relations to these things then make for a book like The Radiant World that its study is the study of effects and phenomena in the emission of radiation and the transmutation of elements. So let's take a look at this for a moment and see kind of what it has in it. David Lillie's Lillie, Our Radiant World, from Iowa State University Press in 1986. It's got radiation, origins of radiation, effects of radiation, radiation in you. Then he talks about Chernobyl, where Chernobyl was an environmental catastrophe where a nuclear power plant failed and exposed the environment to dangerous and deadly and ionizing radiation and of the sort that there's ionizing radiation and then there's actually disruptor sort of spallation and neutron bombardment and these kinds of things. And then other aspects of nuclear power as after nuclear energy, doing nuclear work in a sense. This book then is about radiation is going to be a little bit distinct from electromagnetic radiation, but let's see what it says. Talks about a thought experiment of it's kind of like it's about a caveman, Oog. So it'd be kind of like what's that one allegory of the cave or whatever, except in this one it's got nuclear radiation in it. Uranium, radon, cosmic radiation. And so these are the ideas that even in the allegory of the cave, it's like, well, you can still figure out that there's gamma rays and stuff like that. About radiation here is that there's light and optical radiation, and then there's nuclear radiation for gamma rays after Roentgen rays are a lot the same. Optical light is special, and nuclear light is like a higher power version of that with regards to the opaque, and then the opaque to radiation or what interferes with that kind of materials and processes, because light has no electromagnetic character at all. And nuclear radiation, although it may be ionizing and infected with kinetic, just like light has, bounces off stuff and makes for solar sails. Although that's part of the solar wind is plasma more thoroughly, but for light and solar sails, but for light and energy, that the whole idea of the electromagnetic spectrum and that being the electromagnetic frequency of electromagnetic radiation, according to frequency and wavelength, because we have a particle theory, and so frequency and wavelength exactly defines the energy within a particle, and the frequency and wavelength are inverse quantities. One of those with regards to wave velocity, and the other one with regards, in a sense, to the resonant frequency of things, has that electromagnetic radiation is given to electricity and electromagnetism. Because light has no electromagnetic character by itself. It's in light is optical light is special, and then the nuclear radiation is kind of like that as well. Nuclear particles are different. Like the particles are different than the rays. And this is the usual idea. What is radiation? The term radiation as we use it today includes more than electromagnetic wave types. So the author has given that there's differences. And so it's usually given that, well, the light is kind of given to be for that there, and then for the infrared and up to the ultraviolet, but above that it's out. And so here it's furthermore given that optical light is special. And then for things like, the account of quantum electrodynamics of Feynman's virtual photons as charge carriers are only otherwise there because, well, they're massless and chargeless in terms of them being electromagnetic radiation in electrodynamics, the quantum. So those aren't even photons, anyways, of the visible light sort, and they are different wee beasties of a sort. The supersymmetry is about this tetradic quantities. Kind of has three supersymmetries, and they're basically high, medium, and low. The micro, macro, and meso for the low, high, and medium. The virtual particles are given as after it counts as supersymmetry. Is like, well, what's the grandest thing our giant supercollider can spin up? Let's call that the Higgs boson, and say that's where electromagnetism gets unified with kinetics. And then similarly, it's like, well, actually, we kind of have a model of the atom and the graviton is about the same as soon as they're just kind of going either way in the middle. And then with regards to that versus charge and stuff, it's like that's what all our classical milieu is basically lives on top of that, and that's given all the invariants already pretty much. But as this splits out, then that's like the other things. Then the little Higgs and this kind of thing are three kinds of supersymmetry that make for three entirely different regimes of running constants. For then, and then there are different ones of those with regards to which of the tetradic quantities is kind of primary. And so a theory of heat kind of has it's like, well, kinetics is primary. And a theory of electrons is like, well, electrons are primary. And a theory of muons or what is with the idea that there being one where the nuclear lifetime is primary. And then the fourth one is kind of like, well, light is like a neutrino for anything. It's primary. Now, I know that will seem to have crossed categories for splitting that out, because otherwise our entire theory today is after a special relativity account of electron physics, and it's simply not complete. And so when it reaches that point where, hey, this is crossing across these categories, these tables are distinct things. These things are not like the other. They don't relate. It's like, according to supersymmetry, that's how they do relate. And the idea that it's kind of focused a little pyramid of the standard model of particle physics as the Higgs boson is like, that's always falling back around. Because the Higgs field is not a classical field. The Higgs boson is not a particle. It's a doublet. And an experiment very well carries this out. And there's more talks about that in the past year. Point being is that our classical theory is built upon these tables, and built upon thusly these platform, the planks, the platforms, then the developments, the definitions, derivations in the field. That coming around is that to be replete, all these other ones do too. So here in the beginning of this book, it carefully distinguishes between radiation of the usual sort that people are talking about, and then nuclear radiation, which just isn't present at all otherwise in these usual theories of general relativity and quantum mechanics. They just don't have it there. And so that's I think that's mostly meters, kilograms, and seconds then. But it's for the empirical units in the field, because the standard SI units eventually are just what's left over of the dimensionless of those quantities. So this sort of book, in its introduction, at least helps establish is like, yes, we do make a contradistinction about those things. And yes, the popular account of science and the introductory elementary account of science will not have mentioned some of these things, because that involves a wider and fuller context. But it is definitely so. And while yet it isn't definitely so, then the fields, these are various things in terms of how they unify and are unified. So, and then it talks about frequency and wavelength and electromagnetic waves. Here he talks about particulate radiation. And so particulate radiation also shows up the difference between current and radio waves current, and those being current in terms of changes in the flux of the flow of the models of lines of force of those fields and their forces, their particles. That particle beams like electron beams are different than the electrons holes in the usual sense of radio wave currents. So already, the kind of like laser is different than optical light, behaves more like a stream of particles. Then a stream of electrons behaves more like electrons, and as with regards to being beams of the optical. And so lasers and masers are different than radio and optical light, irrespective. Becquerel, the Curies, Pierre and Marie Curie, early scientists in nuclear theory with regards to radioactive elements, about the scales. Then the particulate radiation again, as regards to the transmutation elements, about things like Cherenkov and Bremsstrahlung or breaking radiation. It's like, why is there light coming off that nuclear pile? And it's like, well, because there's stuff coming out of it, or basically being absorbed into it. That these are the kinds of things that Cherenkov and Coriolis and Compton and Coulomb and Quantum Hall all have different effects that are otherwise outside of these models of the things. They're empirically evident, their effects, which is why they're called effects, because otherwise they'd just be elementary. Hypersonic Inviscid Flow by Wallace D. Hayes and Ronald F. Probstein. Or Propstein. Hypersonic Inviscid Flow. Dover Press, as one might imagine, the Reynolds numbers, which is about turbulence and shock, according to the Mach-ian in the acoustic and about the speed of sound, and that surfaces in the sound crossing the speed of sound would create shock waves off of it. How that hypersonic inviscid flow is part of the ideas of like, well, can stuff go faster than that speed without causing a sonic booms, these shock waves that arise off it? Yeah, maybe so. Or can objects faster in these speeds travel at all without the shear and forces after turbulence disrupting them, tearing them apart? Yeah, kind of like so. And so hypersonic inviscid flow, as one imagines, gets into the mathematics about fluid dynamics, and that's used to model the aeronautical as well, the profiles of drag and these kinds of things, and that the empirical terms are as a sort of like the Reynolds numbers, and for matters of turbulence, that otherwise it's like, well, and then all we have left to solve for it is Navier-Stokes and models of flow, and then and that being continuous models of fluids, vis-a-vis something in the logistical models of networks and graphs that Ford-Fulkerson is kind of our optimum flow. That gives what flows and in what manner. And then in Navier-Stokes and fluid mechanics is supposed to give what flows. Well, as from reading from the book on turbulence theory, it's like it's never that simple. I mean, that's ideal, but it's never that ideal. It's not practical to just think that everything's ideal in the applied in that manner. Well, yet finite element analysis breaks it on down and to a point. And then with regards to the issues like the analyticity and Kodaira and the Zariski and the scope and why those things break on down and get involved in the empirical and the interfaces and the effects, and also in the small, when different notions of like mass, length, and time get to where they're grainy of a sort of indistinguishability. And so then what results as form and as organized out of that has the utter, that's when entropy has already reached to infinity, say. So these are conditions and situations where it may be said, in a sense, that aspects otherwise as governed by entropy have gone to infinity. And so any notion of a discontinuity or shear is kind of that way. And so the superfluid and super conductive, as after accounts like Fritz London and for where it's essentially these other aspects of models of balance of the invariance of like resistance and Ohm law and stuff like that are gone because it's 1 over 0 is infinity, or vice versa. Then getting into the hypersonic inviscid flows involves where that comes back together, because then it would seem that for things like waves and layered media and setting, it was like, well, it's kind of like if there's laminar layers, like if you consider the atmosphere to be concentric shells, and so the layers, and then how something can slide between those layers, and then whether or not it's possible to design the properties of materials, or what the properties of materials they have would be to have that then in their interference with waves are models of change in open system. How then that all these different the phonons in those models in the acoustic of what are like, these are the wavelets of the kernels of the wavelets that are the pops that become the shocks that become the booms, the sonic boom, and how it can be so that then also it won't set up the tribology and the hysteresis of this rheology in a sense of destroying anything going at this speed. That this book is an account as and one imagines a modern and high level account of why that would be so. If one made a railroad track about 200 miles long and angled upwards at about 1 degree grade and accelerated on something at about 1 g, at the end it would be going about 25,000 miles per hour, and that would be escape velocity from the Earth. And then there's an idea is that, well, as soon as that, say that was like a train car or something like that, as soon as that hit the atmosphere, it would be like a belly flop from a cliff dive or something like that. It would cause instant splattering of it. And then as it flew through that, it would burn off. It would ablate all the way on out like a jet, like an ingot. The course of these things. So that's not really a practical thing, but it is sort of a physics problem. The electromagnetic gun launch to space is the idea. And so, well, how could that be figured out? It's like, well, if you do actually just separate the atmosphere, like if you just shoot out a lightning bolt in front of that, then the atmosphere would basically be just dissipated, and then it would shoot right out through that. Nothing to worry about. So a notion of having like using electrostatic and skin effects makes into advanced materials and materials design was what could enable things like hypersonic and viscid flow in usual aerial and aquatic media, and also in the usual ethereal, in a sense. Constant stream tube area approximation, thin shock layers. So thin shock layers, successive approximation schemes. A number of subsidiary relations are needed, including 5.1.1, 5.1.4, and 5.1.8, and with axisymmetrical problems, 5.1.3, 5.1.5. These are criteria of conditions of constraints, pretty much. The pressure, entropy, and streamline inclination as a function of a shock angle, sigma, must be available and are obtainable from the shock relations given in Chapter 1 in the equation of state. So the turbulence for matters of the shear and transverse then is for then the shock relations that this book from 1959, that setting, that's the preface to the first edition, and 1966 the preface to the second edition, that one imagines this book is very well familiar to people in the field of this kind of research, because it's looking to address is like what happens when hypersonic is Mach 5 or 5 times the speed of sound. What happens when something either enters Earth's atmosphere at a very high velocity or leaves or passes? Vis-a-vis viscous and rarefied flows. Talks about Zel'dovich and Raizer, R-A-I-Z-E-R, from the Advanced Research Projects Agency. Karman, Theodore von Karman. The book started as a projected 80-page contribution to Advances in Applied Mechanics. So that'd be something to find. Advances in Applied Mechanics, circa 1957. General features of hypersonic flow fields. The normal shock wave, or is from the shock wave is like it's normal, meaning it's perpendicular to the surface. Oblique and curved shocks. Mach number independence principle. So that chapter 1 is general considerations. Chapter 2 is small disturbance theory. So that's just like that normal move out thing. It's like the virial principle, the small perturbations, small disturbance theory. Monte Carlo in Markov chains. Very, very usual, kind of the idea of that making grounds for approximations of things in the finite element analysis. Newtonian theory, and so Newtonian theory including kinetics and kinematics and the incompressible in fluids. Constant density solutions, the theory of thin shock layers, infinitesimal analysis and finite element analysis again. Numerical methods for blunt body flows, and other methods for locally supersonic flows. So, Mach number independence principle might say something to us here. It gives some constraints to begin about the inviscid hypersonic assumptions are A, mass infinity is greater than and then or equal to 1, or basic hypersonic. B, sine theta b is much less than 1, slender body. C is m infinity sine b is much greater than 1, strong shock. And E is the epsilon, usually is much less than 1, small density ratio. And m sub infinity sine theta sub b is much less than 1, linearization. So that's basically some ideals, and then given the linearization is basically it's a needle of a sort, but it's a needle that with blunt ends. So the shock wave is in the bow or the front of the Mach number independence principle. The definition of hypersonic flow used by Oswatich, Oswatitsch, involved the concept of the basic hypersonic limiting process, capital M sub infinity goes to infinity, and that parenthetically is a lim. On the basis of his analysis of the flow of a perfect gas, he concluded in the limit of very large values of m infinity, the flow pattern and pressure coefficients on a body were independent of the value of m infinity. So m infinity being just the limit of the hypersonic limiting process of otherwise constructive interference that would result destructive interference. So, and that's where it's like it's essentially infinite. But in the acoustic, and that's why the models of the acoustic and the Mach-ian then get applied to models of like relativity and light speed, because anytime you're thinking about, it's like, well, what happens when we've got to try and think about things that are faster than the speed of sound? What happens when you try and get thinking that things that are faster than the speed of light? And so you got phonons vis-a-vis photons. Phonons for the aural, the phonetic, the phonons, sound. Sonons or phonons. And then photons as for light. Then one could think of these in terms of reaching and approaching the speed of sound in a model of that as a space, and reaching or approaching the speed of light and that in a space. And how those then get into why the Mach-ian is kind of the surrounds of the development of what would then go into the Mach-ian in terms of parallel transport and the teleparallel and Einsteinian theories. The definition of hypersonic flow. On the basis of his analysis of the flow of a perfect gas, he concluded that the limit of very large values of m infinity, the flow pattern and pressure coefficients on a body were independent of the value of m infinity. The same result had been found by Sir Isaac Newton for his model of a rarefied gas. We shall restate this important idea in a way which does not depend upon the gas being a perfect one. Cherny, Cherny, credits this principle to S.V. Vallander, Vallander, but gives no reference. 1949. The word similitude usually is used to refer to an equivalence between two physical problems which are different from each other in some fundamental way, but they're alike. Oswatich stated his results as a similitude. An inviscid perfect gas with constant ratio of specific heats is a self-similar fluid, whose Cherny flow field permits the general Mach number similitude obtained from dimensional analysis. The general similitude, expressed by Oswatich, utilizes this property of a perfect gas. When the result is properly restated for a general ideal in viscid fluid, it really states that in the limit m infinity goes to infinity, two flows with different values of m infinity are fundamentally identical, i.e. are not different from each other in any fundamental way. qualitative way, and including as quantitative. It's been gone to zero, the difference. Although the result expressed for a general fluid may certainly be termed a similitude, it is preferable to consider it as an independence principle. Such an independence principle is thus a special type of a similitude, which is stronger than a general similitude. So this is great accordance and agreement with the language here, because the similitude is basically expecting that, well, our reductionist account is something that's entirely ignored in the usual account. It's just not given that it's reduced at all. But it's reduced to make a similitude, like for the equivalence of energy or everything. That's the similitude of then these reductionist accounts. And then the independence is here that's framed in terms of the intentional and the extensional. The intentional means exactly equals, and extensional just means we can't tell different. So, a similitude in that sense. So, and then the notion of the independence principle is that the modal relevance of these is outside than either of the accounts of the way, not including the other. So that this is compatible language is what I'm saying. In order that the flow field may be independent of the free stream Mach number m infinity, it is necessary that at any point on the shock the density ratio E be independent of m infinity. So independent or negligible, or that effectively zero or effectively infinity. These are usual ideas of how that would be with regards to the dimensional analysis. And then for things whether the bounds are from 0 to infinity or from 0 to 1, also whether that's just effectively unity and these kinds of things. Anyways, this book then gets into a lot more developments to have all these kinds of ways to then figure out the curves, show them with their discontinuities, and then having analogies and then methodologies like an artesian well analogy, a shower bath analogy, that make for there's basically two different ideas of Vallander, and he picked one, and so then there's still the other one. The theory of Messiter, Missiter, is the first theory. He considers delta wings, and so as not to repeat his analysis, we present the second theory. Hida, probably Japanese, Hida, has extended the theory of Messiter somewhat. Newtonian, Hoarth Dorodnitsian, variable of Newtonian theory, because then the Newtonian has the incompressible flows, which are sort of ideal, but for gases, the rarefied gas is it's just kind of like constant pressure, constant back pressure. It doesn't really apply. It's independent for a reduction, and approximations are imperfect, while yet often close enough. Edward John Ruth's Dover Phoenix edition, so a nice hardback book from Dover Phoenix Editions, Advanced Dynamics of a System of Rigid Bodies. So here one would expect to find a lot more about the kinetic and kinematic and why they are different. And so let's see what's in them. The advanced part of a treatise on the dynamics of a system of rigid bodies, being a part 2 of a treatise on the whole subject with numerous examples by Edward John Ruth, R-U-T-H, SCD, LLD, FRS, ETC, Honorary Fellow, Peterhouse, Cambridge, Fellow of the Senate of the University of London, Dover Publications, Mineola, New York. First published in 1955 and reissued in 2005 as an unabridged republication of the 6th 1905 edition of the work originally published by the Macmillan Company in London in 1860. So this would have been the advanced part of a treatise on the dynamics of a system of rigid bodies in 1860. And so we got a lot out of the World Fact Book from 1846, about Faraday. It's like, Faraday's discoveries are new. This is how locomotives work, and this is how pneumatic air delivery works. Surprisingly, it's kind of the opposite how you expect they would, is what they found out when they made it big enough. And these kinds of things. So then Ruth here on mechanics and rigid bodies, then for kinematics, because the behavior of rigid bodies is then how they're connected and these kinds of things, and their actions and these kinds of things. One would imagine. Then relating that to accounts of after thermodynamics and the statistical ensemble and so on is that usually all this lives in the classical, the kinetic and kinematic. So it's got gyroscopes, Clairaut's theorem on relative motion, equations of motion on a moving body. So chapter 1 is moving axes and relative motion. Chapter 2, oscillations about equilibrium. So also the gyroscopic and these sorts of accounts. Oscillations about a state of motion. Energy tested stability. So stability, Watt's governor, Lagrange's three particles. Let's take a look at Lagrange's three particles. Page 75. Chapter 4 is motion of body under no forces. And so that gets into all such notions of random motion. Solution of Euler's equations, Kirchhoff solutions, Poinsot's construction, converse theorems when the body is acted on by some forces, impulsive couple, resistance to the air, the polode, Polhode, time of describing an arc, greatest and least angular velocity for the same, what intersections of quadrics could be, the Erpolode, McCulloch's, geometrical transformations of Poinsot's and McCulloch's, geometrical, stability rotation, the conjugate ellipsoid, conjugate line, motion when, the useful spherical triangle. These get into a body of a motion of body under no forces. And so that's a lot of different things going on with regards to what it's doing. Like under no forces mean it's like it's been launched, this tangled, moving, weaving thing, all the kinetic and kinematic actions of it is like, how does it wobble? What are its oscillations and restitutions for attenuation and dissipation? Chapter 5, motion of a body under any forces. Motion of a top, rise and fall, rough ground, smooth ground, resistance of the air. So that resistance to the air, for example, is kind of like a simplification, like that's Newton's for you. It's like, well, it's rarefied air. It's a value that's finite, as long as you're going in one direction. This is like a lot the other things about it. So kinetics and kinematics are two different things, and motion to be ideal, as after Galileo's, is we have our Newton's and Galileo's zero-eth laws of motion to get figured out. And that's for matters that space contraction is evident after third order terms anyways, like for the classical Magnus effect and Hef and for classical mechanics. So it goes. Well, we've reached about an hour, gentle readers. I shall so hope you have a great day. Warm regards.